Hello again. This is the second part of video lecture 28.1, and I'm going to talk about the material in section 2 of chapter 28. And it's really now going to be nothing new in this section. We are going to take a number of ideas we've already studied and put them together. Namely, we're interested in the motion of a particle with some amount of mass, m, some amount of electric charge, q, and it is immersed in both an electric field, such as you would find between the plates of a capacitor, and a magnetic field, such as you would find in the vicinity of a magnet. And we want to be able to predict how such a particle will move. Now we know that the way we predict motion is using Newton's second law, or some related and similar idea, like a conservation of mechanical energy. And so we're going to use here Newton's second law, and force formulas we now know for both electric force and magnetic force. Okay, so here is the scenario. We have a particle. It's got electric charge Q, that might be positive, that might be negative charge. It's got mass m, that's definitely positive. It's moving at a certain moment in time with a velocity v arrow. And it is in the presence of both an electric field E arrow and a magnetic field B arrow. And again, one of the ways you can get the electric field is just put the particle between the plates of a charged parallel plate capacitor. Positive charge on one plate, negative charge on the other. You get a nice uniform electric field in the middle, pointing away from the positive plate towards the negative plate. And put this whole thing near the poles of a magnet. And now you've got a charged particle moving in both an electric field, E arrow, and a magnetic field, B arrow. And we know the formulas for calculating the electric force and the magnetic force on this same particle. The electric force is the easier one, mathematically. F electric is Q times E arrow. We've done that a lot now. And the new one, in the video lecture I just sent you, F magnetic, is given by Q times V arrow cross B arrow. And yes, we're back to vector product that we have to deal with. So we're interested in problems where both of those forces act. And almost always we'll be interested in problems where those are the only forces acting. Almost always. Now, with those forces, then you just predict the motion by solving Newton's second law. The acceleration of the particle, A arrow, is the net force, F net arrow, over m, where everything has to be done with components. Force and acceleration are vectors, so we do have to deal with that. So what I want to do here is just show you a little bit of the motions that you can get when a charged particle moves in combined electric and magnetic fields. And I'm going to focus on a situation that people call crossed fields. Crossed electric and magnetic fields. And what that means is the electric field vector, E arrow, and the magnetic field vector, B arrow, are contrived so as to be at a right angle to each other, perpendicular. That's what crossed means in this case. And that, first of all, gives you some rather interesting motion. And second of all, it simplifies the math a little bit when they're crossed relative to each other. So now I want to go to a Wiley Plus simulation. And again, we know that if we're dealing with magnetic forces, as we're going to be here, we have to think three-dimensionally. So the pictures tend to show, when you're dealing with magnetic forces, an X and a Y and a Z axis. And this picture shows just that. Let me zoom in a little bit. Okay. That should be zoomed in a little bit. Let me center it a little bit more. Okay, I want you to be able to see all those arrows. And what we have are our three axes. We have our particle. It's that red disk that's initially at the origin. We have a magnetic field that this particle is immersed in. That's the green arrow, B arrow. Notice it points in plus Z everywhere. Wherever you are, the B field points in plus Z. And then the red arrow right here is the electric field that this particle is also immersed in. It happens to point in the negative X direction. All right, so I'm going to kind of go back and forth between this picture and my OneNote so that I can write. So when I'm looking at this combined electric and magnetic forces, here's what I know so far. I have a magnetic field vector, B arrow, that is some constant B times K hat. It's in the plus Z direction. And I have an electric field E arrow that's a constant negative E times I hat. That means it's pointing in the negative X direction. And we say that these are crossed E and B fields because they are perpendicular to each other. And of course, now we know how to calculate the electric force, F electric on our particle, Q times E arrow. So that would be minus QE times I hat. Meaning the direction of the force, electric force, is in the negative X direction if Q is positive, but it'll be in the positive X direction if Q is negative. Our animation, go back to that, looks like the sign of the charge is positive. And if I hover over the blue arrow pointing in the negative X direction, sure enough, that's labeled F electric. Same direction as E, which is the red arrow. Okay, so everything makes sense so far. All right, next, what can we say about F magnetic in this particular situation? F sub B. Well, we have to do Q times V cross B. Let me draw my own sketch. And one thing you probably will need to realize, back to the picture, is that the velocity vector, V arrow, is that red arrow right there. There it is, V arrow, pointing in the plus Y direction. So the velocity vector, let's come over here to the side. X, Y, Z, as our particle. There's its initial velocity vector in the plus Y direction. And the magnetic field vector B that the particle's in is in plus Z. So let's get the magnitude first. FB magnitude. Sorry, let's make sure you can see what I'm writing. That would help. Okay, so notice I've drawn the X, Y, and Z coordinate system. The velocity vector is in plus Y. The magnetic field's in plus Z. I'm now working out the formula for the magnitude of the magnetic force. That's magnitude Q, magnitude V, magnitude B, sine of what we call theta, which is the angle between V and B. You see that that is 90 degrees from our picture. Sine of 90 is, of course, 1. By the way, the animation says Q is positive, so I don't need the absolute value on that. So there we go. That's the magnitude of the force. A lot of books would then just write that like that, where everything is a magnitude. Oh, Q is positive. Let's get the direction, though. That's just the magnitude. What's the direction of the magnetic force? Well, first find the direction of V cross B using the right-hand rule. Well, there's that picture. There's the V, and there's the B. Practice, please. Use the right-hand rule and try it and see what you get. Pause the video and come back. Okay, so when we do V cross B, I take two pens, red and green, red for V, green for B. I do V cross B. My thumb points along plus X. It's got to be perpendicular to the plane of V and B. So let's be careful. Now that's the direction of V cross B using the right-hand rule. Then you get the direction of the force. Depends on whether Q is positive or negative. If Q is positive, the force magnetic is in the same direction as V cross B. Well, that's what we've got here. So FB is like that. So my final expression for the magnetic force is QVB I hat. So here we go. I've got an electric force in the negative X direction and a magnetic force in the positive Y direction. Let's go back to the animation and see if that pans out. I've already shown you that that arrow is F electric pointing in negative x. There's another blue arrow right there. Let's see what it's labeled. FB, plus x direction, F magnetic. They are indeed in opposite directions. Since they're in opposite directions, there's a chance that those two forces, F electric and F magnetic, will balance each other, giving us a net force of nothing at all. Let's see what has to be true for that to happen. Okay? So to balance the forces, well, I need their magnitudes to be equal. F electric equals F magnetic. So Q times E like that, which means the magnitude of the electric field, equals QVB. Again, everything is a magnitude. Of course, the Q's cancel, and what we'll do is we'll solve this for V. That will tell me what the initial speed of the particle has to be in order for the net force to be 0. Right? If the V of the particle, the speed of it, is equal to whatever number this ratio is, then F electric and F magnetic balance. We're assuming those are the only forces in this animation. So F net is 0. So the acceleration is 0. So the velocity will then be constant. So even though two forces act on this particle, an F electric and an F magnetic, if, and it's an important if the V of the particle equals the value of E divided by B, then the particle will travel straight line constant velocity. And first of all, it may be a bit surprising to you that the unit of electric field, Newton per Coulomb, divided by the unit of magnetic field, Tesla, is equivalent to meter per second, right? It's a V, it's a little v, but it is. And in the animation was designed so that the E over B is equal to 1 in SI units, so 1 meter per second. So if our particle speed is 1 meter per second, then the particle will travel in a straight line. See over here to the side, it says E magnitude over B magnitude equals 1 meter per second. And look up at the initial speed. Notice what I've got it set at, 1 meter per second. So when I run the animation, what should the particle's motion be like? Think about that a minute. Did you say it'll just travel in a straight line at constant velocity? Let's see. And sure enough, that's what it does. It travels in a straight line, happens to be the plus y direction here, at constant velocity. If v, the speed, equals E over B. All right? Such a device, by the way, is called a velocity selector, because only particles that have the correct speed, v equal to E over B, in this case 1 meter per second, will indeed travel in a straight line like this. Any particle traveling faster or slower than this magic speed will get sent along a curved trajectory, not travel in a straight line. Okay? So let's in fact run the animation for a speed larger than this magical speed, if you will, and a speed smaller than the magical speed. So let's run for a initial V of 2 meters per second. All right, now with V larger than the magic value of E over B equal to 1 meter per second, and the V is what determines the magnetic force, remember, F magnetic is QVB, we start out with a magnetic force that's bigger than the electric force. And sure enough, there's the arrow for F magnetic, and you see it's twice as long as the F electric. So in this case, the initial net force is in the plus x direction. The particle is going to start accelerating in the plus x direction. Its velocity vector, therefore, is going to start swinging from plus y towards plus x. But as it does that, its velocity changes, and therefore its magnetic force changes. So the motion can get pretty complicated. The electric force part is constant, Q times E. But the magnetic force is changing because the velocity is changing. So let's just see what kind of motion we get in this crossed field situation when the V is larger than the magic value of E over B. Wow. You get these kind of sharp cusps in the trajectory. It stays in the xy plane. And it's got this kind of circular looking part. It's not actually a circle that touches the y-axis at discrete points and has those cusps. That trajectory is actually something called a cycloid. Now, let's reset. And let's change the initial speed to be 0. Just initially. Now I have an electric force, constant, and no magnetic force. So it's initially going to accelerate in the direction of f net, which is negative x. But then its velocity is going to change. And so it's going to have a magnetic force. And that's going to be changing. But the electric force is constant. So let's see what kind of motion we get now. We get another cycloid, but it's on the other side of the y-axis. Okay, so you can get motion that is, yeah, I guess you could say you can get pretty complicated. Let's get the largest B we can initially. Oh, wow, 5 meters per second. That's going to make the magnetic field much larger than the constant magnetic force, than the constant electric force. Let's see what kind of trajectory we get now. Okay, wow, that's pretty impressive. Now, this was just solved by having the program solve Newton's second law. A sub x equals F net x over m. A sub y equals F net y over m. All right? Some of those equations have to be solved numerically, but there are a lot of programs that can do that. But there's no mystery what you do. You have the formula for F electric. You have the formula for F magnetic. Those are both vectors. Okay? You add those two vectors to get the net force, and then A, acceleration, equals F net over m. Now, if you want more information about crossed fields, please feel free to read 28, section 2. There's more information there. And then we're going to talk about this kind of application of the magnetic and electric forces in our next class. But that's all for this video.